headset on, so I'm back again. And we finished up the last time around. We finished up with we had completed the two parametric tables and the plots. We did the NPSHR curve, and we came up with a slightly different number. This is slightly different from what we saw when we did the curve fit while we're doing the table. I want to show you how that came about, and it's actually better to do it this way. So instead of using the table curve fit function, we're going to make a new plot window, an XY plot of V dot English versus NPSHR English. We're going to go back to the same boundary condition, 0 to 1,000 and 100 increments of 100 gallons per minute. And we're going to go to 0 for the minimum here, 40 for the maximum. So it'll match our other ones. When we flip back and forth, we don't get any loss of perspective. Interval of 5. We'll put grid lines in. I forgot to check one of those before. No harm, no foul. Fat line. Spline fit. Automatic update. Table 1 was our data for the NPSH required. We don't want point labels. We don't want to connect the last point. We'll do that in systems. And we'll click, make it a nice red line. It's on its own diagram. Click OK. So we've got this curve again. So now what it's going to do is it will use this as a variable, this as a variable, this as units, this as units when it does a curve fit from the plot. So we do a curve fit from the plot, and we say we want a third order polynomial. Normally it'll default to 1. I was looking at it before. We bring it to 4. We want to curve fit it. Our x value is v dot in English. Our y value is NPSHR English. And units are GPM and feet. So instead of having an x equals and various things proportionate to y, we've got NPSHR equals English equals 3.55 feet minus etc. So the other thing is, so include units, copy to the clipboard, place it on the plot, yes, 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 plot, okay. So now this is a little bit too big to fit. I know from having played with this that 24 will work. It just fits. And since I copied to the clipboard, when I paste it over here, it's the same equation. Proper units, proper exponentiation, proper everything. If you don't do that, the way I used to have to do it was copy this equation, copy this. It copies over. Let me just show you. Oh, I didn't copy it. Let me do that again. Command C. Click OK. Come on down here. Command V. Now it looks good, except that's not an asterisk. And that doesn't raise it to the second power in the equation window. So if we have it copy it to the clipboard, when we create it, it puts it in the proper format for the equation window. So let's get rid of this excess stuff and move along. What we want to do now is make a single point solution. We want to know what the crossover point is. All right, so the way we do that is we're going to make a new tab in the equations window. We're going to add the tab, and we're going to say single point solution. Okay, make a new tab. Also, just a little housekeeping. I'm going to go ahead and look at our parametric tables. me name these so that we've got this as NPSH R data. Okay. And table 2 is, we should call that NPSHA. Calcs. Okay. So now, if we were to make a plot of that, say we want to make a new plot, XY plot. Now it's got named, so we don't have to remember which number is which. So that's a convenient thing to do. Okay. So we did that. Nice little bit of housekeeping. In the meantime, for our single point solution, what we want to do is we'll just copy all this given data. And we will paste it in here. Okay. And we're not going to be running parametric tables, and we don't need volumetric flow rate. That's what we're going to be calculating. If you want to do a parametric table later, that's fine. You can do that, and you can compare what the single point solution is for each of your temperatures that you're concerned with. You could even do a plot of NPSH cavitation point based upon the temperature and what flow rate it would start to cavitate. So let's go ahead and copy over some additional equations. So I'm not sure where I left off. I have the NPSH A equal to NPSH R English, and it's in the single point solution. We got rid of V dot because we're looking for the flow rate at which that occurs. We left the conversion because we're actually going to search for English V dot, and that's fine because we use that in our NPSH A calculation. So everything will work out. There was an issue. Let me go ahead and calculate 20 equations in 2 blocks. Everything is fine. 6.026 feet. That looks good. Let's just change this to 60. Recalculate. Okay. 5.468 feet. And if we look at our curves, we had so around 6 feet, a little over 6 feet. Okay. And 5.4 feet. So that's about right. Okay. So we could make this bigger and have closer refinement on here, but we don't need to, right? It confirms what we did. The issue I did have, though, that you may have if you're following along and copying along, is it would come up with an error trying to find a negative logarithm. So what I ended up having to do was, I think Reynolds number was the culprit. I did a couple of different things, and I didn't want to spend the time on this video troubleshooting it. But what you need to do, so I paused it. I came in and I made Reynolds number 0 as the minimum instead of negative infinity, and 10,000 as a guess. All right. Let's just try. What happens if I make it 1,000? Make it laminar flow. Click OK. As a guess. See if it still pulls it in properly. It should. And it does not. So it's basically pulling in. It has a constraint issue. So better off, we'll leave Reynolds number at 10,000 for now. and it will work for any turbulent flow. I mean, set it for 4,000, see what happens. That should still work. Reynolds number 4,000. Okay. Calculate. Continue. Nope. So it needed to be up higher because it's doing something down there, whether it's searching for doing its iterations. Let's go back to 10,000. And I'll be perturbed if we have the problem still. But we'll see. And everything is good. So, and look at where our Reynolds number is. It's 925,000. So I'm not sure why. The way it guesses is it brackets things. So it'll start with a number, and if that number is off, it'll jump to the other side of a midpoint that it's looking at. And if it drops down too low, you can have issues with logs of negative numbers or other things. And that's a harder one to figure out because there's multiple variables inside the parentheses for that log calculation. Anyway, that worked, and it works. We proved that it works. So now we've got a single point solution, and we've got our parametric table and our graphic solution, and I'm going to leave it at that. I will be working on your homework assignment. I'll go ahead and put these on Teams, which you won't know until I actually put them there.